if you're writing on the chat, so if you don't want to speak, but you want to like communicate, you can write on the chat. Like I have a second window that allows me to see the chat, and so I would be able to see your comments. And I think if Victor, if it's ready, I would start.
Should be working now, I think.
Okay. Okay,
I'll
so
check the YouTube channel, but yeah.
Okay. Yeah. So I did the introduction already. Yeah. I did the introduction already. We are skipping, so we are not going through the paper by itself. I prepared the presentation. The paper starts like with an introduction on mechanistic interpretability, which I think most of you are aware. And then it talks about the types of open problems, and in particular, it makes these five broad categories of practical applications of Mech Interp. It's sorry, I need to. There's something on my screen that I cannot see. That you can see, but I cannot. Sorry, let me stop this. Yeah. Let's do it again. Okay. Yeah, and so the five broad categories that they define as possible practical applications of Mech Interp are applications where you try to monitor AI systems. For instance, like a good broad question that would characterize this type of applications is, can you monitor the cognition patterns and detect dangerous behavior while it is occurring? They give a couple of examples. In practice, the current way that we do evaluations, for instance, is very black box. You don't look at the model internals. You just look at for instance, the prediction of the model, and so it's hard to evaluate if the model is doing deception or if it's sandbagging on the evaluation. And so one type of practical applications would be, can we make evaluations a bit more white box and look at model internals to try to understand the cognition patterns that they're doing. They also mention trying to do anomaly detection. The way they frame it, and I think that's normally the framing, would work similarly to like content moderation. So you'd be monitoring the internals of the model, and if a kind of pattern would emerge that's not a normal pattern that you have seen, that would flag the system, and you look better at the model to see what triggered this behavior. And the third type of monitoring application that they mentioned is the ability to improve red teaming effects. If you're able to understand better what leads to deception and sandbagging and have anomaly detection, you can probably develop better red teaming effects. For instance, they mention the work on refusal vectors and using optimized prompts that minimize the refusal direction instead of optimizing prompts to minimize refusal also works. And so this is a kind of mechanistic interpretability application that then improved red teaming. The second big practical application is in Modify AI, where they talk about activation steering, machine learning, and in general knowledge editing, but also fine tuning. It can help all this mechanistic interpretability can help understand how to improve current methods of control and inspire others, like the case of activation steering, which was a mechanistic interpretability work. And it can also try to understand more fundamental questions. And in particular, the example that they give about fine-tuning is that we've seen that fine-tuning, especially, for instance, refusal fine-tuning, is very shallow. And mechanistic interpretability can help us understand why it is shallow and if there's ways to improve it and to make fine-tuning more robust. The third point is about predicting AI behavior. So can we predict, for instance, out of distribution behavior or future capabilities that a model can get from training or fine-tuning? They mention using the Mech Interp to identify Trojan models or models that have been in such a way, in some way like modified in a hidden way, and try to use Mech Interp to find those, but also understanding better adversarial examples and why jailbreaks work. And in a broad way, one of the like the Mech Interp dreams would be to be able to make a synthetic program that reproduces model behavior, and this would be like the best possible case of being able to predict the model behavior, because now you have a synthetic program that's much easier to analyze than a large language model, for instance, and you'd be able to study all the let's say program boundaries and try to understand what inputs would lead to catastrophic outputs. They also mention that, and maybe this is a bit of an area, at least on my end, that I don't know so much, but trying to use Mech Interp to look at emergent behavior, both on scale or on fine-tuning. So taking a network that was unable to do a task, and then a network that is able to do a task, and maybe the only difference, they were trained on the same data, but one of the networks is bigger than the other, or both of them are the same size, but one was fine-tuned and the other wasn't, and trying to understand if it's possible through mechanistic interpretability to measure the difference between these networks and pinpoint better techniques that would allow you to predict if a given network can have a certain ability without measuring that ability per se. Then the fourth point that they mention is improve AI. Sorry, these names are names that I gave to try to make them all the same, but the central question in the box is closer to what they talk about in the text. In Improve AI, they mention using Mech Interp to better understand how to do distillation of models. For instance, by correctly locating some circuits, you could potentially make a smaller model that has the same behavior as the bigger model, but just on that specific task. And so you could make smaller models from bigger models, which would be cheaper to make inference on. They also talk about, for instance, skipping layers because you know the computation is almost finished, and also designing better architectures if you're able to understand which kinds of components make certain tasks. You could start designing components that have those inductive biases heightened, and so that could help you design better models. And then the fifth type of practical application is what is microscope AI. So using what language models or any kind of model learned about the world, and by doing Mech Interp, you extract the knowledge that the model has about the world, and hopefully you learn something new. One of the examples that they give, and they give several examples, but I think this one is the one that maybe is easier to understand, is the fact that when they first trained AlphaZero, they were able to teach some grandmasters new things about chess that they then were able to to put into practice. And they have an example which I now forget, but I think in the example that they give, it wasn't exactly Mech Interp. They just looked at the model doing moves and analyzed that. But in principle, for instance, if you can do interp on AlphaFold, you could potentially learn more about chemistry and biology and on why the proteins fold the way they fold. I don't know if anyone has. I think I'm going to stop on every slide, on almost all slides, because they're very dense and I talk on them for a long time. So if anyone has any question, like specifically about these practical applications, you can do it now. If not, I'll go to the next slide. Okay, so as I said, the paper broadly splits Mech Interp into two kinds of ways to do Mech Interp. One of them the authors call reverse engineering, where you take a network and you try to take it apart into smaller components that don't have to be exactly the components of the network. They can be some kind of abstract components. And then after taking it apart, you try to describe the component interactions that lead to the behavior. And so from the network, you kind of like extract possible meanings that the network has. The other broad approach is what they call concept-based interpretability. And in that case, you think about some concepts and you look for them on the network. Like you're trying to understand if networks understand the concept of gender, for instance, on language, or plurals or adjectives. So you set up in mind with a concept, and then you try to identify which components in the network produce have the roles that produce the kind of behavior that you're looking for. And we're going to be this week we're going to be focusing on reverse engineering, and then next week we'll talk about concept-based interpretability. The idea of reverse engineering, as I mentioned, is that you want to be able to first decompose a neural network. The idea and the picture is that you want to be able to take apart the network at the joints such that if you know every piece of the network and then you know the interaction that happens at the joints, you should be able to decompose the network completely and explain it. The decomposition part doesn't have to be across architecturally defined points. So initially, Mech Interp, and this is something that we'll see also on the next slide, focused on using neurons, for instance, as the basis of decomposition. But you could think of doing decomposition in a more coarse-grained way, looking at full components like the MLP or attention at a given layer. You can even be more coarse-grained and consider full layers. Or you can do something that's not based on any given layer or any given neuron, but a combination of them. And the way that they define reverse engineering mechanistic interpretability is that first you do this decomposition, you describe each part of the decomposition, and then you make an hypothesis on how this decomposition makes a certain makes the process that you're trying to analyze, and you have some tests. You try to validate this hypothesis, and if you're able to validate the hypothesis, you're good. You explain the network. If you weren't able to validate the hypothesis, you go back and you try to find either better descriptions or different decompositions. As I was saying, initially, one of the first tests was to use neurons as the natural decomposition, but as maybe most of you know, neurons are polysemantic, meaning that if you look at their activations, they activate in examples that may not have a single meaning for a human, and so after that, other kind of techniques started to develop. The author mentioned using dimensionality reduction on different parts of the network, but the problem with using dimensionality reduction is that it is not useful to deal with superposition. So the idea of superposition is that networks want to represent concepts with their parameters, but they want to represent more concepts than dimensions that they have, which means that some dimensions can be more than one concept. And so when you do dimensionality reduction, you will always be in superposition, and you cannot take these concepts apart. And because of this, recently people started working with sparse learning, so with sparse autoencoders. If you're familiar with that, the idea is that you go from a lower dimensional space, let's say the residual stream, the output of the MLP or the output of attention, and you train a special simple network that goes from that dimension to a much larger dimension in a sparse way, such that you can identify individual dimensions that are active, and hopefully these intermediate dimensions are interpretable. And because of like this technique has seen a significant, let's say, success. Everyone is doing it. There's multiple ways of doing it. You can do sparse autoencoders or transcoders or crosscoders. The authors mentioned the different techniques. The problem is that these techniques there's multiple things that are not completely explained. One of them is that their reconstruction is too high. They talk about how, for instance, when people from OpenAI trained sparse autoencoders on GPT-4, the reconstruction of those sparse autoencoders, even though they had 16 million latents, was the same as having trained the model for only 10% of their data. So it's like they're throwing away 90% of their model by using an SAE, a single SAE on a single layer, which is obviously too much alignment tax. And even when you do this on smaller models, on models like GPT-2, you can get performance drops of 10 to 40%. And so developing new techniques that improves the reconstruction errors seems to be something important if we want to continue using sparse models. Another thing that they mention as a problem is the fact that it's very expensive to train sparse dictionary to do sparse dictionary learning on large models, especially if you want to have an autoencoder or a transcoder that has a large number of latents. You may end up having a more compute intensive than the original layer that you're training on. And so if you want to do something, if you want to decompose every component of the network, you might end up having to train a new model, basically, in terms of compute, to explain the base model. And this is obviously not feasible for large models where companies may be compute constrained. They also mention the fact that we are assuming the linear representation hypothesis. So we are assuming that it's possible to linearly read the concepts that the model uses, and that this have any sense, which is obviously partially, it has to be partially just an hypothesis, because the models are nonlinear, and so and we keep finding ways that models represent concepts that are a bit more complicated than just the linear representation hypothesis. And so it's possible that we are losing something by using sparse dictionary learning. The other thing that they discuss is about sparsity not being the best proxy for interpretability. The reason why sparse dictionary learning works, or the idea behind it, is that can go to a higher dimension, and then by making activation sparse, you can look individually at each activation and try to understand what's happening. The problem is that as you make models sparser and sparser, you start getting an effect that's called feature splitting, that they represent here by originally having just a direction for cats, but then you start having a direction for Persian cats and Siamese cats and Maine Coons. I think that's what's written there. And also you start having feature absorption, where before you had a feature that was begins with E and then a feature for elephant, but because you're constraining for sparseness, the model learns a feature for elephant and a feature for begins with E except elephant, so it no longer activates on elephant, and the elephant feature absorbs a bit of the begins with E feature, and this just makes latents less interpretable, because now what looks like an elephant feature can bring with it some other baggage. They mentioned that it's not straightforward to apply sparse dictionary learning for all models. For new architectures in the future, if people start using Mamba or start using other models, we may need to think about where to train our sparse autoencoders. Even on transformers, it's not obvious how you deal with attention heads, where do you train it, and this is something that they mention. Another problem is that even though sparse dictionary learning describes activations, it doesn't completely describe the mechanism that the model is using. So it's not looking at the weights of the model, and it's not understanding why that input gives that activation, or why that activation leads to a certain output. And they in this section they talk about maybe looking at weight interpretability instead of just activation interpretability. Then I skipped one. Well, I skipped two. So the related to the linear representation hypothesis is the fact that sparse dictionary learning completely ignores that there could be some kind of geometry in the place where the model is being trained. And for instance, it has been observed that models represent time like in a circular way, where you have features that are more than one-dimensional, that are two-dimensional, and that rotate, and the model represents January next to February next to March, with just some angle separating them. And current.
I want to mention like this a recent paper by Max Terman and his students, where they found that also seems like numbers for addition are also representing some kind of it's also a circular thing, but it's like some spiral thing. I haven't read the paper yet, but it's something like that. It's like related to the modular addition example, but the modular addition thing was on like very small models, and this I think it was on actually large language models. And that's the kind of thing that you might miss if you're just doing sports encoders. Although at the same time, you will still get like a feature for each number. You just wouldn't get the thing you wouldn't get is that the features are represented in some way that's related to each other in a way that like probably matters for the actual computations. But yeah.
Yeah, so you'd still get the direction for January and still get the direction for February, but without you having to look at it specifically, you would not see that the direction for January and the direction for February are related by a certain.
Maybe there is some way of like if you have a bunch of features that you got from person encoders, you can like so there is some automated way of finding like if some of them are related in some kind of interesting geometry. But I don't. It's not obvious that you can, but maybe it is possible to do something.
Yeah, and then the next thing that let's say it's not the last problem, but another problem that they mention is that it's possible that in your training data or just because of inductive of the biases of training, the concept that you are actually trying to look for is not captured by the SAE or the other dictionary learning model that you trained. And you can think about this in a very simple way. For instance, if you train on data that doesn't talk about biology, you will never learn any concept related to biology. And so then if you're trying to evaluate the model in some kind of biology question, your SAE will not give any interesting results, or you'll not be able to use your SAE. They finally mention that we don't have like a strong theoretical basis for any of these. So we still aren't sure if the linear representation hypothesis is even a good approximation. We don't know if superposition is a concept that actually makes sense, or if it's just like an apparent thing that we've been able to use. And they describe a couple of different more theoretical frameworks that should be pursued, but that are still, let's say, in infancy, and it's not obvious how they relate with interpretability. And they end the section mentioning that it probably makes sense that you try to embed some of these advantages of dictionary learning right into your models and make them interpretable. For instance, using a mixture of experts or using sparser activation functions. They talk about using bilinear activations in MLPs to make interpretation of them easier. And they give a bunch of examples on techniques that would make models interpretable, and they present these as kind of an alternative to the problems of sparse dictionary learning, because hopefully if your models are more interpretable, then you don't need to deal with polysemanticity or with superposition. After you decompose the network, you're obviously not done. You still need to describe what each part of the network does, and you need to describe the interactions between the different parts. They divide this problem into two parts. The first part is understanding why a component activates, and then the second part is understanding what the component does in terms of downstream effects. And so if you're able to do this for all the components that you care about, you can do this kind of causal tracing, where if you want to explain what this model does, you look at all the inputs, you look at all the outputs that are activated by these inputs, and then you look at all the outputs of the node that you want, and finally you'll observe the output effects. And if you're able to explain all of these, you can describe what this component is doing. They start by talking about using looking at activating examples to try to explain the input of models, and describe some problems with using activating examples. And then they describe attribution methods as well, that and they give a list of several different attribution methods, most of them that are gradient based, and they describe some problems with using attribution methods, and now there are to interpret, but mention that efficient and accurate attribution methods is an open problem that's very important if we want to be able to describe components. And then they mention a strategy that kind of combines these two. So looking at activating examples in nature, let's say, and using attribution to make what they call feature synthesis, where you try to produce artificially synthesize highly activating data, and through this process, it's possible that you learn about what the component is doing, but some criticisms about doing this instead of just using natural data sets. Having explained the input of your component, you may want to explain the downstream effects. They talk about 3 different ways that you can learn. Yeah.
Really? Maybe maybe Bart and I should head first. People want to head over.
You have your microphone.
Okay.
No. Sorry, I'm going to mute this person because they have the microphone. Sorry. Okay, I was talking about the output behavior. They talk about studying 3 different effects. One of them is the direct effect. If you know about the logit lens, the idea is that you can look at what the output produces, what the component produces, and try to expand it as if it was already the end of the network, and look at the effect. And they talk about different variations of this. And this is a direct effect because you see what the component does without passing through the network. Then they talk about indirect effects, and especially about doing causal interventions, where you patch parts of the network with different values of the component, and you try to observe the kinds of paths that through which the information passes, to try to understand what the component does. And they talk about different methods that are all of this type of causal interventions. And they talk about some of the drawbacks of this, that for each intervention, you kind of need a forward pass. And if you have a lot of components, and if you have of different things that you want to explore, this may become very expensive, and instead they mention some kind of interventions that use gradients to approximate the normal causal intervention to try to better understand the downstream effects. And finally, they talk about looking at the effects on a sequential kind of way. So instead of just looking at the direct effect, so in the case of language models, instead of looking just at the next token, you see how that effect propagates for longer across multiple token positions. And they talk about how you could basically patch the forward pass of a model into a different part of the model, so like into a future forward pass, and try to see what kind of influence that has in model behavior. Finally, the third step of reverse engineering is, let's say, the fundamental step to close the process, where you try to see if your hypothesis about your description of the different parts and their interaction makes sense. They give different ways where that you'd be able to do this validation. One of them is if you're able to predict the activations of certain parts, you can then make predictions and check if your description matches with what we observe. For instance, in sparse dictionary learning, you may have a component, so a certain feature on your sparse autoencoder that you think activates on text about cats, and so you can, if that's your hypothesis, you can pass through the model a bunch of text about cats and see if indeed predicting that it activates on cats actually predicts the behavior that you observe on that data set. In a similar way, they talk about how you could look at adversarial examples and failure modes and understand if by doing adversarial examples that your description is still valid. They talk about handcrafting a network. So if you're able to describe the circuits and all the components of the circuits and how they interact, you could just make a network that has that part of the circuit and check if the circuit is able to perform a certain task, or if you have access to the ground truth. So if you're able to make a network that by hand, that you know the algorithm that the network is implementing, you could test out some kind of interpretability technique on that network, and if you find the real algorithm, you know that that technique is probably good. And they end the benchmark on the hardest kinds of things that you can do, which is you have a certain engineering goal, like you want to make sure that that models refuse, or you want to understand why models make a certain bug in code, and you use your description to fix that problem in a way that's competitive. They talk about how most interpretability models are still far away from being competitive to other methods that you may use to fix a certain engineering goal. finally, they talk about making benchmarks and designing a parallel to the Drosophila in biology. If you don't know what the Drosophila is it is a kind of, it's an organism that's very simple and that people can, if they want to understand some kind of mechanism in biology in living things, they normally look at Drosophila to kind of understand what kind of processes it makes. And so they talk about the possibility of creating more modular organisms that are made to have certain behaviors, and then you could study them and check if your hypothesis generation tool works or not. And this has been the part on reverse engineering networks. The next 3 slides that I have just about like these open problem. It's more than 3 slides. It's 6 slides. And so I think it would make sense if people have questions either about what I discussed or if they read the open problems, that we can now talk about them. I think in general, I mean, the way that I presented most of these problems that are open, I mentioned them like briefly. And so if you have any questions, or if you read the problems and you think they were interesting, just say something. Otherwise, I don't think it's so interesting to just to go through. There's not that much to discuss. I mean, just if we have something to discuss about them, they make sense to discuss. But otherwise, reading them doesn't bring much information. I don't know if people don't have any questions, I think we can wrap it up.
I guess I can comment something just so it's not just to say something. So the division between like the reverse engineering and concept-based interpretability seems like a not super natural like division to make, seems kind of arbitrary. I guess it doesn't completely not make sense, but still feels like the things that they put there is like there are some techniques that are still motivated by trying to understand the model, and yeah, I don't know. Mm,
I also agree with you, Victor. It seems like quite arbitrary in the sense that, but rather if you then read the description and the text for the figure, you probably like have a better understanding. But yes, the drawings are not that clear to me, at least. And also because we are hypothesizing that the models learn something always based on some kind of concepts, right? Otherwise, it wouldn't make any sense, like try to interpret anything inside the models, right? So it's like we are just starting from that hypothesis. So like,
I guess you can think of it. I guess it's not thinking about it is not that unnatural, because you can think of it as the first kind of thing is like the thing they call reverse engineering is like something like unsupervised finding, like trying to find features in the model, and the thing they call concept passive interpretability is like have a human think of specific things they want to look for in the model. And so I guess in that sense, like there is some distinction there. Those seems like two different methods. Yeah, I guess yeah, they both have different ways of doing things. Not like necessarily the way you can divide things up, but yeah. I guess another thing I thought when reading this paper, not only this part of the paper, was that the I they have a section of the thing that Gonzalo called like practical problems or something like that. They call it they call practical applications. They don't call it that on the paper. They call it like types of problems of problems. And that seems like a weird, like it's. I think it makes more sense to talk about in terms of applications, because these are basically things you can use Mech Interp on, while like open problems to me are more like the kind of thing you will divide in. I feel like there are some more divisions that you could do than just whether they are reverse engineering or not. You could talk about, there are open problems that are about how we divide the how do we divide the modeling features better? Something like maybe you do better sports encoders, maybe you do whatever the new Apollo research thing is that I haven't read that paper yet. That's supposed to be like a replacement for sports encoders, or you do whatever dimensionality reduction. And a separate another kind of problem is once you have some features, how do you do attribution of them, or like how do you find circuits of them and how they are connected and what the features are used for. Also, yeah, when you have one feature, this kind of later but not exactly the same, what some feature means in some sense, which that's where you get some kind of problem. You get the kind of techniques that you get with auto kind of when they use ChatGPT or whatever to generate explanations for feature in Europedia and the related OpenAI paper. So like in general, and the paper talks about all these things. It just feels like it's not organizing it the way I will organize them. Which I mean, it's not that bad a problem. It's just kind of it's not ideal, but in the end, I for what I'm saying, it still like talks about everything it should talk about, just in kind of weird order.
Yeah. So about like this division between reverse engineering and concept based, I think like one of the things that you said is probably the best way to look at it in terms of supervised versus not supervised. When you're doing reverse engineering, you're just trying to find everything that the model has, while you're doing concept based, which we didn't explore and we'll talk about next time. Their idea is more of supervised methods where you do probing and stuff like that. In terms of this thing that you were saying, I think the way that they thought about the paper was more what are like big open questions, like theoretical open questions, and in this section, that section of the theoretical open questions, they called it open problems in methods and foundations, and then they have and next section, that's the open problems, the practical applications. But I agree that it's a bit like their types of open problem section is a bit weird. The way that it's framed, it's a bit weird.
Yeah. No, specifically, it's framed about applications rather than about problems in Mech Interp, in a sense, I feel. But yeah. Anyway, another thing, like talk about the supervised and unsupervised thing. I feel like you could also you could also mix the two. I think it might make sense. For example, I mean, think of trying this. Maybe it doesn't make sense for some reason. I haven't thought, but like doing probing on like the sparse encoder like features basis to see which features are encoding some human concept that you want to find on the model, and you use probes mix up with sparse encoders to like trying to find which sparse encoder features might correspond to the thing you are looking for.
Yeah, like in SAE benchmark, they do something like that where they train probes on SAE activations, on the sparse activations of SAE. Yeah.
Because I've been thinking of doing something like that for the chess, Lila
I mean,
chess.
they weren't the one that introduced that. Someone else introduced that, but in SAE benchmark, they link to the correct source.
Yeah, I'll probably look at that. Yeah, I just thought of it, and I knew this probably either it doesn't make sense for some reason I haven't thought, or someone else had already done it. So I should just go look at what other people have done. Yeah.
Okay. So if there's nothing else, because we already arrived to our mark.
Yeah.
I
don't have anything else to say. I mean, I was to somehow just talking right now to see if it will create some discussion, but I'm fine with leaving it here.
Okay, so next season, next week, we'll do the rest of the paper, and then from then on we'll talk about non-review papers.
Stop the